In this video, we'll be going over concepts that we learned in part one of buffer concepts. And this time we'll be using a little bit more math and going into trying to show what the numbers mean, like when you're calculating the pH of a buffered solution. So um, here's our problem. So as you know from our previous video, that this is a when you have conjugates, so you have HF and you have NAF. Okay, and this of course is not going to really do anything. So basically, what you have is F minus. So you have a weak acid with its conjugate base. So this is the conjugate base of the weak acid. And if you have those in significant amounts, and this would qualify as a significant amount probably, then you have a buffer. So this says calculate the pH of a 1 liter solution of zero point 0.1 mole HF and zero point 0.1 mole NAF. Next, it says calculate the pH of 0.050 mole HCl. And then in our third calculation, we're going to calculate what the pH would be if you added 0.050 moles of NaOH. So here we're going to add a strong acid, and in the next problem, we're going to add a strong base to this mixture. And if you recall from our previous, from part one of buffer concepts, the main idea of a buffer, like the main purpose of a buffer, the purpose of the buffer is to consume strong acids or strong bases and resist pH change. Okay, consume as much of it as it can and resist pH change. So and then what we're going to do after is compare and contrast the results of all three calculations. So let's go ahead and work these problems out. I actually started doing this problem, or actually one of these, I actually started doing in the previous video, but we're going to carry out the whole problem here. So number one is before anything. So this is number one is no strong acid or strong base. Okay, and this one we're going to add some strong acid, and then in part three we're going to add some strong base. So in our first one, this is before anything is added, so no strong acid or strong base is added yet. Okay, so then we have, so as you see, we have a buffer already, so we could carry this out in an ice table, but the whole purpose of the Henderson-Hasselbalch equation is so that we can, it's kind of like a shortcut, and it's based on an ice table and the assumption that X the amount of dissociation is negligible to the amount that you have. So we're just going to go ahead and use the Henderson-Hasselbalch equation because we see that we have a buffer. We have a weak acid and its conjugate. So, and it's a 1 liter solution. So they're together in a 1 liter solution. So pH would equal pKa. So the pKa of HF, which we'll be using in each of these problems, is 3.14. So this will be 3.14 plus the log of the concentration of base over acid. And so you'll see an interesting thing happens here when you have equal concentration conjugate and equal concentration of the weak acid. So this would be the log of 0.100 over 0.100. This has a important this is an important detail of buffers, and we'll see this come into play when we do titrations. So the log of this is the log of 1. So the log of 1 is 0. So an interesting thing happens when you have it in equal concentration, the two conjugates. So pH actually equals pKa, which equals 3.14. So pH is 3.14. So this is before anything was added. This is number one. Okay, number two is we're going to add some strong acid. Okay, so here's our reaction. We're going to have um, the H plus. This is from the HCl, plus. So we have to choose. Okay, so it can react with. So here's our mixture here, and this is our strong acid. So we have to choose what's the HCl, what's it going to do? What's our strong acid going to do? So this guy is a weak, this is our weak acid, and then this is our weak base, the F minus. So it's going to be strong acid, and the weak base is what's going to interact. So we have H plus and the F minus are going to react and make HF. So it's actually going to form the conjugate. So we'll set up a earth table. Our H plus is 0.050. Our F minus is 0.100. And we do have some HF initially present. We have 0.10 moles, so we need to put that number here. So we'll write 0.100 moles of that. This is our limiting, so minus 0.050. Reactant side. Here's our product side, so we're going to add 0.050. This goes to completion. The H plus is completely consumed. We have some F minus left over, 0.050, and this goes to 0.150. So now we have a buffer still, and it consumed all the H plus, so now we're going to write, so pH is equal to 3.14 plus the log of base over acid, so 0.050 over 0.150. Okay, so you should actually, this is actually the technical way to do this, is you should actually do this before this piece right here. You should do before entering in your calculator. So this actually is 0.33, 3, etc. You should only have two sig figs here, so you should have 0.33 here. So you're taking the log of a number with two sig figs. So that should have two decimal places. So this is 3.14. And you'll see that if you take the log of a fraction, you actually get a negative number. So you get negative 0.48. And we'll discuss this at the end, when we address question 4. Okay, so what's going on here? So this is 2.66, your pH. Okay, so now we have on our third problem to do here, we have, we're going to add some strong base. So now, if we add some strong base, so we have strong base. This time, it's not going to interact with the weak base, of course. Our strong base will interact with the weak acid. So our reaction will become this. It's going to be OH minus plus HF. And we're going to get F minus plus H2O. Okay, set up our earth table. And this is 0.050. This is 0.100, 0.100, and water doesn't really matter. Okay, so this is negative or minus 0.050. So our strong base will be fully consumed here. And this is going to go down to 0.050, and this goes up to 0.150. All right, so now we're ready to calculate the pH. We see that we still have our buffer because we had enough of this to consume all of the OH and have some left over. So we still have our buffer. So this would be 3.14 plus the log of base over acid. So this time it's 0.150 divided by 0.050. Okay, so this result should be 3.0, so 2 sig figs. So the log of that will have 2 decimals. So this is 3.14. And this time we're taking the log of a whole number, okay, not a fraction this time. So it's going to actually be plus 0.48 this time. Okay, so our pH will be 3.62. So let's now address this question here. It says compare and contrast the results of all three calculations. So if we look at our original buffer, so this had no strong acid or base added, so our pH was 3.14. Now we ate through half of the conjugate. We ate through half of the conjugate base. So we had 0.1, now we only have 0.05, but look at the pH. It really didn't change that much. Okay, not even half of a whole pH number. So it went down because we consumed half of the base. So we have more acid than we do base. So we'll see that our pH ended up being a little bit lower than what our pKa was. And this happened because we took the log of a fraction, so we were subtracting here. So there's a couple of things to point out here um, as a result of this. So we took the log of a fraction, first of all. Log of a fraction means we subtract from the pKa. In other words, probably a better way to say that is we had more acid than we did base. Okay, if we look at our fraction here, we have more acid than we do base. So what's the result of that? Is our pH goes down, which makes sense. It's more acidic, so pH should go down. Okay, and this is because the pH or this so what ends up happening is the pH actually is a little bit less than the pKa because we were subtracting from the pKa. Okay, now let's take a look at our the reaction with the base. So this time we took the log of a whole number this time. So log of a whole number means we added to the pKa. So um, so you see that we add here, and so our pH is going to end up being a little bit bigger than the pKa, which makes sense because we have this makes sense because we have more base than we do acid, so our pH should be spike up a little bit slightly, okay, very slightly. So this time we have more base than acid, so this means our pH is increased, so where our pH is greater than pKa. Okay, so why don't you guys go ahead and try um, the next the next question. It's very very similar, so you guys go ahead and work this problem out and see what you come up with. Okay, that's the end of our tutorial.